Hello, everybody. I hope everyone had a good Wednesday. I managed to finish our lab assignment for next week, so I have posted that, but I don't think I've revealed it yet. If you can see experiment number 4, that's probably because I pushed a button that I shouldn't have. It shouldn't be there. It will appear next week. You may see in the playlists on my YouTube page the video for experiment 4, and that's okay if that shows up. But don't worry about that. It won't be assigned until next week. There is no lab due next week. There is, however, a lab due tonight, and that is experiment worksheet number 3 that we went over last week, the Beers Law one. So make sure that you are finishing that up and submit it before the deadline. I will do a last call tomorrow at some point when I start downloading them all, and then I will grade them. Other things to mention, I have not fixed the grades yet for the midterm. That is the next thing to do after I finish writing all the labs. I do have another lab for another class that I am writing, and I'm about 50% of the way done on that, so hopefully I will have grades updated and fixed by Friday. I think that's it. I think that's it for announcements. So let's go to this slide. And oh, I have other little tiny things to look at too. So let me see here. What does my list of things to do for 161 say? It says finish lab worksheet number 4. I already did that, so let me type done. Check for stray or lost lab number 1s and 2s. Oh, that's right. I wanted to mention that. Some people are using NQA coupons for labs. Make sure that if you are planning to NQA a lab, you do 2 things. One is you email me to say that you're going to do that so that I put a blue square in your gradebook instead of a yellow square. The gradebook being my Excel file. And then 2, when you finish it, send the lab report directly to me. Don't upload it to Canvas if you're using an NQA, because I don't notice it. It doesn't give me an alert that, oh, somebody uploaded something. If you have already done that and you uploaded your lab number 1 or 2 or whatever late, I'm going to send an email out to anybody who I don't have a lab for. And if you uploaded it to Canvas, just email it back to me. That's fine. I'm sure that if I clicked on your name individually, it would tell me when it was updated or uploaded or whatever. So I can verify that you aren't turning it in like 4 weeks late. What else do I have to do? I had to check an exam 1 question. I had 1 question that I had to throw out. And then check quiz 2 number 3. I have something written down about... I think I put the charge of an electron was wrong on something like that. So I have to edit that score too. So there is a list of things to do, and I worked down the list. But I also have the same list for a second class, and these things do take time. So I apologize that it is going slower than I would like. We are halfway done in Chapter 3, thankfully. This is the part where it all starts to come together. We have talked about how to represent orbitals in space, what the quantum numbers mean, and now what we're going to do is we're going to put all of this information together with your periodic table. So make sure you have access to a periodic table for today. www.ptable.com is a good one. If you have your textbook, there's one in the back there too. Let's go ahead and get started. So when we talk about all 4 quantum numbers, NL, M sub L, and M sub S, the thing that is described by that is a specific electron in a specific orbital. And so what we're going to do is we're going to abbreviate some of these quantum numbers, and specifically we're going to indicate these 2 using a code to describe where the electrons are, what energy sublevels. And the way that this is done is we write something called an electron configuration. And so an electron configuration represents where the electrons are for an atom in its default state. And the default state is what's known as the ground state. The ground state is its lowest energy possibility, where the electrons normally are. Now, if you add energy to the electrons, like we've been talking about with light and heat and stuff like that, then what ends up happening is they end up in an excited state. And an excited state is a higher energy state than the ground state. Now, there's two ways to do an electron configuration. There is the sentence, and then there's the diagram. In class, I would make you do both, but it's very hard for me to assess diagrams. Like, I have that hotspot question where I can make you click on something, so I might, like, draw a diagram and say, tell me where the last electron goes, or something like that. And you have to click on the diagram. But I can't make you draw a diagram in Canvas. Like, that's the only thing I can do. So, I'm going to be drawing a bunch of diagrams, and it's in your best interest to practice drawing those along with me. But when we don't want to draw it as a diagram, we can instead explain the electron configuration as a sentence. And the way that we do that is to write it like something like this. And actually, if I just hit the spacebar, all my indicators are going to come up here in a second. But the way that we write an electron configuration is that we want to have our electrons go into the lowest possible energy levels and then fill them up to progressively higher and higher and higher levels. And the way that we do this is the first thing you write is the energy level n, so that's going to be a number or an integer. The next thing that we do right here is we write the letter code of the sublevel. And then finally, as a superscript, you put the number of electrons that are in that energy sublevel. So for instance, if I wanted to write helium, which has 2 electrons because it's the second element, I would write 1s because that's the lowest energy level, and then I would say 2 because I'm allowed to have 2 electrons per orbital. But if I wanted to do lithium, I can't do this because that would violate the Pauli exclusion principle. I can't have 3 electrons because 2 of those electrons would have the same spin. So what I have to do is I have to fill my orbitals with 2 electrons, and then I have to go to the next lowest energy level. Well, there aren't any other possibilities for 1s, so the next one would be 2s. And I only have 1 electron, so I would do that. And I know this ordering because I know how my quantum numbers should be arranged. So I know that for n equals 1, there is only one possibility, L equals 0. And for L equals 0, there is only one possibility, M sub L equals 0. And then M sub S would be these 2 electrons here. Over here, I know that N equals 2 is the next lowest energy. For that, there are 2 possibilities, 0 and 1. 0 is lower in energy because it has a lower quantum number. And then for 0, the only possibility for M sub L must be 0. The next one would be for this quantum number, which would be -1, 0, or 1. And this would be 2p. And so I'm going to actually arrange my energy levels in this order. It's just going to go 1s, 2s, 2p, 3s, 3p, 3, and so on and so forth. Until we hit a certain point around calcium where the energy levels start to blend together. And we'll talk about that in a little bit. So there's helium. That's what that would look like. Oops. I could give you any element, and you should be able to write the electron configuration by just filling in electrons with the smallest, not the smallest, I'm sorry, the lowest energy orbitals filled first, and then you progressively go from there. I want to just peek ahead which ones I make you do in a second here. Sorry. Okay. I'm going to show you all that in a second, but what I want you to do in the chat is I want you to tell me the electron configuration for these elements. So draw sulfur, and also do carbon, and then we'll say, let's do aluminum, and then neon. So in the chat, type in the electron configuration, and what I would do would be something like this. So if I had to do, for example, beryllium, here's what I would type in the chat. And you can see that I have like a space between those, just so like you don't get a bunch of 2s in the way. So type in the electron configuration, write it down on your paper first for each of these elements. And we'll go over the answers in just a second. Anybody got sulfur? You want to type in the chat here. We might need to do another example. All right, let's try doing another example. So I'll do sulfur here. So remember how for our quantum numbers... And yeah, I do want the whole thing, so no shortcuts yet, because we haven't talked about what that means. So remember how for our quantum numbers that we could translate these into things like this. And that to change that into a letter code, this would be something like 1s. Because for L equals 0, that's S. And then L equals 1, that was P. L equals 2, that was D, and so on. So hopefully we remember that. If you write out all the possible quantum numbers, when you get to here, that's 2s. That's 2p. That would be 3s, and then so on. So you know the energy level because you know that lower n's are lower in energy, because we saw that in the Bohr model. So you put the electrons in the first n because it's the lowest energy. Then you put them in the second n because it's the next lowest energy, and so on. So for sulfur, what you would do, first you count the number of electrons for sulfur. And on the periodic table, it's element number 16. So it has 16 electrons. So we need to put 16 electrons in this sort of structure somehow. And the first 2 are easy because we know where those go. 1s2. Then the next orbital would be 2s2. Then the next orbital would be 2p. But how many different orbitals are there for 2p? Well, because I have 3 m sub l's right here, that means I have 3 places to put electrons. In other words, I could hold 6 electrons there. And now I just keep going until I've used up all 16 electrons. And there you go. That's as far as you would need to go to get to 16. Well, I hope so. 2, 4, 10, 16. Okay. And for carbon, that's exactly right. Also, carbon is 6 electrons, so I fill the lowest energy, I go to the next level, and I keep going until I run out of electrons. There you go. So following this pattern, do aluminum and neon. And then type them in the chat when you are done. All right, I see an answer for neon, and that's correct. Very good. How about aluminum? What do we got for aluminum? And that's correct also. 1s2, 2s2, 2p6, 3s2, 3p1. There you go. You got it. Now, you could see that the order is just like, oh, I'm just going to remember this order. 1s, 2s, 2p, 3s, 3p. But where does the order come from? It comes from these quantum numbers, which we talked about. Okay? And what we're doing is we're just arranging them by energy, lowest to highest. And we know already that the lowest energy must be anything with n equals 1 in it. And then the next lowest energy must be anything with n equals 2 in it. And then n equals 3, and then so on and so forth. Now, later on, we're going to answer the question, why do I put S before P? Like, why is S lower in energy? And unfortunately, your textbook doesn't really talk about it that much. I'm going to tell you the reason for it, and then you're going to be like, that's a bullshit answer, I don't understand. Do we need to know that? And I'm going to say no, because your book doesn't talk about orbital penetration at all. So let's show this on a diagram. So the way that we do this is that we sort our energy levels just like we did before when we were talking about the Bohr model. We have n equals 1 down at the bottom, n equals 2 is in the middle, n equals 3 is higher, and so on and so forth. On each level, and I'm going to have to erase this in a second, we're going to draw boxes, and the boxes represent orbitals. And then underneath that, I am going to label the orbital with what it is. Now, I like to put it in a bin when I start teaching this, just to let you know, oh, these guys are together. But eventually, I'm just going to stop drawing these bins. Like, for example, if I had to draw 2p, what I would do is something like this, and then I'd put 3 of them. And I guess I'll just do this to make the diagram complete. And again, these orbitals come from quantum numbers. So this would be 1, 0, 0. Oops. I missed my parentheses there, but that's okay. This is 2, 0, 0. This would be 2, 1, negative 1. 2, 1, 0. 2, 1, positive 1. And as a review, we draw the number of boxes that we draw in each sub-level is the number of possible values for m sub l. So I had 3. There was negative 1, 0, and 1. So I drew 3 boxes for a p orbital. because there are 3 orientations. And hopefully this is all starting to kind of gel together. Like, oh, I kind of see where that is. Eventually, what you're going to do is you're just going to forget that all these quantum numbers ever exist and just draw the diagram. And that's fine. All right. Oh, I got to clear my diagram here because now my structure is appearing on top of it. And now what we're going to do is we're going to take our diagram and we're going to put electrons in there. So this is for helium. Helium has 2 electrons, and I'm going to put them in the diagram. Here they go. Whee! There goes the first one. And then there goes the second one, except there's an issue with this. And the issue is that as I have written these, they have the same spin, and that violates the Pauli exclusion principle. So I got to do this. Boop. And now the diagram is correct. So that would be for helium 1s2. And I don't know if I put that on there. Here, let's just do it like this. So this is my sentence, and this is what it represents as a diagram. Now we can do this for more complicated atoms. In fact, we can do this all the way up to atom 118. We just make a progressively bigger and bigger diagram. But drawing a diagram for 118 electrons would be ridiculous. It would take a lot of time. Now, when you get to n equals 2, you do have to worry about S, P, D, F, etc. For example, n equals 2 as L equals 1 is a possibility. And in L equals 1 or 0, those are 2 different shapes, S and P. And so we have to worry about sublevels. The way that the ordering of sublevels is the following. S is always lower than P, which is always lower than D, which is lower than F. But there is a caveat to this. So this is true within an energy level, or in other words, within an N. So for instance, 2s will always be lower in energy than 2p. But 2p will not be lower, or 2p will not be, or sorry, hold on. I drew the wrong thing. So this up here will be true, but this won't be true. And the reason for this is because they're not the same N. So we can't compare the energy levels of these directly. But within an energy level, 2s and 2p order like this, and this will always be true. 5s will always be below 5p. 4s will always be below 4p. And then 4p will be below 4d, and so on. Alright. So let's consider that when we draw our diagram, and then I'm going to tell you, or actually I'm not going to tell you why that happens. I'll tell you why that happens when we get to talking about 4s, because that's when things start to get scrambled up. So here's our n equals 2 diagram. I'm going to put 2s down. And again, here's that orbital's quantum number. And because there's only one possibility for m sub L, I only put one orbital. For L equals 1, that's 2p. There are 3 possible values, so I draw 3 orbitals, and there they are. Now, because there is no 2d orbital, since I can't have L equals 2 for n equals 2, that's all I draw for n equals 2. The n equals 2 orbitals are complete. And so now what I can do is I can start putting stuff in there with regards to my electrons, and I can put all my electrons in these diagrams. But there are some things that we want to talk about. First of all of these orbitals right here are at the same height on my diagram, so they go to the same point on the y-axis. Whereas this guy down here, 2s, this is lower in energy than these. And the reason for this is because of what we said before. S is lower in energy than P. But what about the individual P orbitals themselves? Well, they don't differ from each other than their orientation in space. They're exactly identical. And so what we say is that these orbitals right here are what are known as degenerate. If something is degenerate, it has the same energy as the things around it. It's basically a fancy jargon-ladled way to say these are equal. So you might hear the terminology, oh, they're degenerate, thrown around in physics and chemistry. All right, let's start putting some electrons in here. So here's oxygen, and oxygen has 8 electrons, 8 total electrons, because it's element number 8. So we're going to put those 8 electrons here, and in they go, boop, boop, boop. Now, I get to this point, and it's like, what do I do? I filled in the first 4 pretty easily, because it's 1s2, 2s2, and then I go 2p. It should be 2p4, but do I do this? Oops, sorry, I'm wrong end of the pen there. Should I do that? Or is there some sort of quantum mechanical physics sort of thing going on here? How do you determine n when we are only given electrons? So we determine n based on where the electrons just go. So if I only have 2 electrons, that's all n equals 1 can hold. If I have more than 2 electrons, I need to use n equals 2. And if I have more than however many electrons n equals 2 holds, then I have to go to n equals 3, and so on and so forth. So you just start at 1 always. Because n can be any number you want, right? Because remember, from the Bohr model, we arranged n levels by energy, and the closest to the nucleus was the lowest in energy. That was n equals 1. And then it went up from there, n equals 2, n equals 3, n equals 4, etc. And that's what we do. We just fill in the electrons, starting with n equals 1, and then you continue from there. Now back to our question on here. Let's suppose that I have 3 orbitals that are equal in energy. You can think of this as like 3 apartments that have the same rent. If you were an electron, would you like to move in with a roommate or by yourself? You're going to pay the same rent. Which would you like? Now remember what properties electrons have. They have a negative charge. Now even though they can have opposite spin, they still repel. So if the opportunity for them to be unpaired exists, then they will do that. And so this is known as Hunds Rule. If I have extra electrons that I can put in equal energy orbitals, in other words, in degenerate orbitals, I do one at a time first, and then I go back and start pairing them. Now that's too many electrons, because oxygen only has 8 electrons. So here's where the next 2 would go. And then the last 2 would be, I fill in the 3rd orbital, and then I pair any one that I want. Because they're all degenerate, I could pair any of them. Convention is we work from left to right. However, you are not required to do that. So if you instead did this, that is also correct, because they're degenerate. You can put it wherever you want to. What you can't do would be to pair these 2 first. And the reason that we don't do this is because electron-electron repulsion says, no, I'm going to move one of them over to a free orbital. Don't leave orbitals free on the same energy level without before you pair them. All right, so there's our finished oxygen atom. And again, this is called Hunds Rule. Hunds Rule basically says put 1 in every box on a level before you start pairing them. And there's our electron configuration, which we wrote out before. Maybe we did do oxygen. We didn't. That's okay. All right. So what I want you to do now is here are my 3 examples. I got fluorine, phosphorus, and argon. And what I want you to do is I want you to first write the electron configuration as a sentence. And then I want you to try drawing the diagram where you have this diagram, so the energy diagram. Okay. So draw your orbitals, label them as 1s, 2s, 2p, etc., and then put the electrons into those diagrams. You should have 3 diagrams for these 3 elements. Okay. Once you have finished all of that, type in the electron configuration in the chat. Even if you see other people doing it, type it in anyway. And then we'll go over the answers in just a second. So it looks like I see a mistake on that answer. So you could put 2 electrons in each box. How many boxes are there for 2p? That looks better. So keep going. All right. Hey, people are using the chat. This is good. I don't want to say anything because I want you guys to actually have a discussion. And it looks like people are getting the right answers. So let's go over how this works. Oops, that didn't quite catch what I wanted. That's probably okay. All right, so first let me write the electron configuration. Where can I write? I can write. Let me just do this so I know I don't want to go past that. All right, so we'll do fluorine first. So fluorine has 9 electrons. And we know it has 9 electrons because it's element number 9 on the periodic table, and everything is neutrally charged, so it must have 9 electrons as well. So we fill them in from bottom to top, so lowest orbital first, 1s2, 2s2, 2p, and then I just need to put the remaining electrons, which is 5. Now I got to draw that on my energy diagram, so I'm going to, oops. This is the part where it's like, what do you use this tablet for? Certainly not art, right? That's good enough. So there are our orbitals. We do 1s is the lowest, 2s and 2p should be above that. 2s is lower than 2p because we said s comes before p. And then we fill in our electrons. So we've got 1s2, so I put 2 electrons in here. 2s2, so I go 1, 2. 2p5, I go 1, 2, 3. Because of Hunds Rule, I fill 1 in first. 4, 5. And so that's what my diagram should look like. All right, let's do phosphorus. Phosphorus has 15 electrons. And I go in order from lowest energy, 1s2, 2s2, 2p6, all the way up to highest energy. And how many do I have left? 6, 8, 10, 12. Looks like 3. So for phosphorus, I would just extend my diagram. And the order is SPDF, that's right. So let's see here. I had 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15. That's what it would. The electron diagram would look like for phosphorus with 15 electrons. And then finally we got argon. Now you do the same thing. 1s2, 2s2, 2p6, 3s2, 3p, 6, 8, 10, 12, 6 is 18. There you go. And then for argon, I would just put in the next 3 electrons, 16, 17, 18. Now, I've run out of room on the paper here. I could just pick up the diagram or extend the canvas or do something like that. But the next question that we're going to ask ourselves is, what happens when we go past 3p? What's the next orbital that we should fill? And you might say, oh, it's 3d, because that's the next available orbital. And it turns out that normally you would be right. However, when we fill in electrons for our elements at high ends, an interesting thing happens. And we're going to discuss that in just a second. First of all, here's the actual order. Oh, I didn't actually tick over to the slides here. Here's the actual order in which orbitals are filled. And you might be looking at this diagram and going, holy shit. But in reality, this is actually very straightforward. I have written all of the orbitals for S, P, D, and F like this. So S is in its own column, P is in its own column, D is in its own column, and F is in its own column. And then I've just numbered them from top to bottom with which ones exist. So there is no 1p because I can't have L equals 1 for N equals 1. And the way that you do this chart is you just simply cross them off, going diagonally down and to the left. And every one of these that you pass through, if you could draw straight lines on your tablet, that is, boop, 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 you write them in the order that you pass through them. So the order of all my orbitals would be something like this. 1s2, 2s2, 2p6, 3s2, 3p6. And so where am I? I'm right here now. So the next one would be 4s2. And then the next one after that, we'd go loop around over here to 3d. How many electrons are in a d orbital? Think about the quantum numbers. How many electrons can I put in there if I could put 2 per orbital? How many electrons can you put in a d orbital? A lot is not quite the answer I wanted to hear. 10 is correct. How did you get 10? Well, if I look at something with L equals 2, that would be D. The possible values of M sub L are -2, -1, 0, +1, and +2. And if each of these holds 2 electrons, that would be 10 electrons. I mean, you could also look at the next slide, yeah. Anyway, what comes after 3d10? So we did that, so now we're at 4p. And 4p has 6 electrons in it. Then 5s. And then you just keep doing this until you get all of the electrons that you need for whatever element that you were looking at. Is there a minimum required for D? Yeah, you had to have at least 1. And you also have to actually get up to that point. So, for instance, the first element that has a d electron is scandium, so it's number 21. And that's because to get to that point, you have to put in the first 20 electrons, which would be these 20 right here. 6, 12, 14, 16, 18, 20, and then so the next one would be in this spot. I don't know what I did, but it beeped at me. Alright, so let me erase all the ink on the slides. Alright, so the term for this is called the Aufbau principle. That is the German word for filling up. And what we are doing when we put electrons into our configuration, either the diagram or the sentence, is that we fill them up from the bottom to the top. Lowest in energy to the highest energy. Even though this diagram is written in the opposite order, that's just for a mnemonic, so you aren't like trying to read from bottom to top. That would be weird. Alright. Now, why is this the order? There is a phenomenon called electron penetration that your textbook barely covers. And what this really means is that electrons in high energy orbitals have very unusual electron probabilities. And I'm going to try and do the best that I can to explain this over here. So let me scroll down a little bit here. Where's my pen? There it is. Okay, so if I look at my orbitals, so this was an s orbital and this is a p orbital. Specifically, this was a 2p orbital. And if I wanted to make a 2s orbital, I have to have a node in here. Now, if I were to draw a graph of the probability of finding an electron, so this symbol squared, this is psi in Greek, and this just stands for probability of finding an electron. And this down here was the distance from the nucleus, where the nucleus is right here. For a p orbital, I would not find any electrons at the nucleus, because that's where the node is. But it would be more likely to be found out here, further away, and then it tapers off as you go further away. So for p orbital, it looks something like that. And so that would be 2p. Now for 2s orbital, I'm going to mostly find my electrons in this outer area here. So I would have a high probability like this. But there is some probability that my electrons will be found closer to the nucleus in this area in the middle. And so what that does is the probability hump ends up doing something like that. And you'll notice that for this peak, for 2s, and this is the peak for 2p, 2s is actually closer to the nucleus than 2p because of this part in here that's behind the node. The electrons are allowed to be there. And because we can equate where electrons are in terms of their distance to their energy, we say that 2s is lower in energy than 2p. And that is entirely because of this effect of the node, and that is called orbital penetration. And so because of orbital penetration, this is true. So this is the quantum mechanical reason why this happens. And do you need to know it? Not specifically for this class, or probably ever. I don't know how many people I go up to and say, hey, do you know why 2s orbitals are lower than 2p orbitals? Absolutely. Well, actually, no, I do that for a profession. I tell you guys that. But, like, in your everyday life, like, nobody gives a shit, right? But for a quantum mechanic perspective, or a chemist or physics major, someone who's really interested in this stuff, this is actually really important. There is some probability to find my electron closer to the nucleus for 2s than for 2p. And as a result of that, 2s is lower in energy than 2p. The same thing is true for 3s, 3p, and 3d, but this diagram that I draw here would get more complicated. So if I had 3s, 3p, and 3d, s would be lower than energy than p, which would be lower in energy than d. And the same thing would be true here. Now, the reason that I went from 2 all the way to 4, and I don't know if I have enough room to keep going here. I could probably squeeze it in the corner here. Is, if you remember our diagram, I was drawing so well, and then that was the line I drew. If you remember something from earlier that looked like this, n equals 1, n equals 2, n equals 3. Remember this diagram from the Bohr model? The effects of this orbital penetration, what they end up doing is they end up taking these levels and kind of spreading them out like this. So here would be 2s, and this would be 2p. And this right here would do this. Here's 3s, and then 3p would be in the middle, and then 3d would be up here. And then this would do this, and then you'll see, oh, the energy splits, but because these are so close to each other, the order of my orbitals gets all screwed up. And so, while this is true right here that I'm underlining right now, it does not become possible for us to predict what the orbital order is past 3p without using the aufbau principle. Because everything kind of blends together, and so it's like, oh, well, what is the actual order? And it turns out the actual order is that on the screen right there. So past 3p, you start mixing up your orbital order. And the reason for that is because of this effect of orbital penetration, where the electrons have a probability of being closer to the nucleus. So they change their ordering from S, P, D, and F. And so S is lower than P, and etc. But that spreading, when the energy levels are already close together, like n equals 3, 4, 5, etc., causes them to mix together. So 4s will actually dip down to where n equals 3 is. Now, the last thing I want to talk about, and this is actually going to come up on the lab that you're going to do next week, all of this only happens when electrons are present. Or in other words, electron penetration needs electrons. If there aren't any electrons in the orbitals, you aren't more likely to find an electron closer to the nucleus. And so that actually leads us to a really interesting consequence. What happens if I just don't have electrons? Do all of these orbitals have the same energy as shown on this diagram? And it turns out the answer to that is the following. If you have electrons in here, what I should have just done was copied and pasted what I had before. So this splits down to 2s, and here's 2p. 1s is just right there. This splits down to 3s, 3p, 3d. And then this splits down to 4s, and so on and so forth. And I ran out of space, and so the ordering becomes very interesting. So that happens with electrons because orbital penetration is occurring. But without electrons, you can't do orbital penetration because there are no electrons that have a higher probability. And so what ends up happening for when there are no electrons is the orbitals just look like this, like we saw before. And so even though 2s and 2p are still here, and 3s and 3p are up here in 3d, if there are no electrons in the diagram, or at least no electrons in these orbitals, there's no splitting. And so what that means is, for a very simple atom, like, say, hydrogen, which only has one electron, there's my electron. So anything that would be in n equals 1 would have orbital penetration, but n equals 1 doesn't have that because it's just 1s. So I can take this electron, and when I advance it to a higher level, like we did at the start of Chapter 3, we don't have to worry about s or p or d orbitals because they don't really exist for hydrogen. They're there, but they're all degenerate. But once you start putting in electrons in there, all the degeneracy breaks, and then everything starts splitting into different energies that you can see. One of the things that you're going to look at in the lab that I have for you to do next week is I'm going to give you an energy diagram where you calculate the energy values on the axis for these different orbitals based on what atom I give you and then what you're observing. And the example that I show you is sodium, and it shows an electron going from 3s to 3p. And it turns out that transition is yellow light that you can see in a sodium lamp. This is why we have like yellow street lights. It's because we have sodium vapor lamps. But the reason that S and P matter for that and not for anything that we did at the start of quantum mechanics when we talked about hydrogen is for this reason. When there are electrons present in these orbitals, all the orbitals split. But when the electrons aren't present, they all mash together and become degenerate. All right. Now, that is probably well beyond the scope of this class. However, I feel like explaining that, instead of your textbook just having that yellow highlighted word, it literally says one word about electron penetration. But explaining that in 10 minutes is probably useful because now you can review the lecture and be like, oh, okay, I sort of get what's going on here. You don't have to totally get it because, again, I've been studying this for like 20 years. But if you understand that, like, oh, something happens with electrons, so these are in a different order than what you'd think, that's good enough for me, I think. So what we're going to do, here's the correct ordering of energy, and so this is along the y-axis. I'm going to put a practice problem up on the board, and what I want you to do is fill in the electron configurations for these atoms, like this. Well, actually, we're due for a break. I'm trying to get the break on the timer here. Let's just do this after the break. So if you want to try and draw the electron configuration for zinc over the break, you can go ahead and do that. I'm going to put the title card up. I don't have the timer up. Hold on. I misspelt live split because I don't have a shortcut on my desktop for some reason for it. Not that. Timer. There it is. Alright, so I'll start the timer. We'll take a break, and I will see you in 10. Wah, 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 wah. I'm actually looking at the frames, or I can't really tell because I can't see 60 FPS in my eyes. But like you can see in the that it only seems to be putting out like 1 or 2 numbers in the hundredths place at any given time. And I'm always just like, well, if it doesn't show me a 0, there's nothing I can do, right? I have no idea if that's true or not. Where am I going? I'm going here. Alright, so hopefully you wrote out the electron configuration for zinc, and I have Discord over the chat. I need to move that. Are there 14 electrons in F? There are 14 electrons because... How come? Why would there be 14 electrons in F? Oops, I have to authorize that. I haven't even asked the question yet. Somebody just wanted to really wanted to write out the uranium one. Because there are 7 m sub L's. That's right. Yep. So for m sub L, or L equals 3, for L equals 3, which is F, m sub L could be -3, -2, -1, 0, 1, 2, or 3. That's 7 different things, and in 7 different orbitals. And so 7 orbitals can hold 14 electrons. So for zinc here, we would just do this. We'd go start from bottom to top. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How many electrons does zinc have? 30? This is 20. 20, and then so 3d10. There you go. I could have just hit the arrow button. That's fine. Now, someone wanted to do uranium, and so if you really wanted to, I was going to say someone's going to have to type it in the chat, but somebody already did. And so you would just do this until you got all the way up to 92 electrons, and so you'd have something like that. And I see where the mistake was made, but that, for the most part, what you typed was very close. Now, that's absurd, right? Looking at this down here, if I asked you to type this into Canvas, I would get, like, 48 wrong answers, because there's no way that you're going to be able to do this without making a typo of some sort. And how the hell would you find your mistake? So, for example, in the student's response up here, like, if I had to grade this and I was like, oh, is it right or wrong? I immediately saw that there isn't a 7s in there. And so I know that that's where the mistake was. But, like, what if, like, the 6 in the middle was a 5 on accident or something? Like, it's very easy to make mistakes, and then they'll just disappear into this muck. So there's got to be a better way, right? And the better way is that we're going to take shortcuts. We're going to come back to these problems to do them with shortcuts on another slide later. But here's how we do a shortcut. If I wrote up barium like this, here's its electron configuration. What I could note is that part of this is the electron configuration of a noble gas. And the specific noble gas that is xenon, and that's right here. So here's barium, and what I'm going to do is I'm going to take this highlighted yellow part, which represents xenon, and I'm going to substitute it in for this. Just like in math, I'm going to just call it a variable. And there you go. That's the better, shorter way to write these electron configurations. Now, what that does mean is that you have to know where you're going to start in the electron configuration. And that's going to require you to use the aufbau principle. Steve, stop messaging me. God damn it. Oh, Steve had lecturing issues. Steve is a Oh, you can't hear the little ping because I've muted the audio. Okay, so I'm just complaining about Steve. Steve also teaches at Everett Community College. Apparently, he just had a disaster, and I'm going to have to help him as you guys do problems. Anyway, this does require that you know where you're starting from, and you can use the periodic table to do that a little bit. I need to actually pull up a periodic table so I can show this to you. So, p-table. All right. Is my window capture... No, it's live split. I want this one. Why isn't it... Oh, because I didn't do that. Okay. Okay. It's too big and I can't select it. Why can't I select it? There we go. Okay. And that's actually what I'm going to show you right now, is how do we become familiar enough to know where the shortcut is? And the answer to that is, see these numbers on the side that I'm highlighting right now? So this 1, 2, 3, 4, 5, 6, 7. This is the number for the period. And this is always S. Okay? So this element right here for cesium is 6S. This element here for potassium is always 4S. And since that is always going to be where you start after using the noble gas configuration, you just look at what row you're in, and that you start with that one, S. So if I wanted to do calcium, it would be brackets argon 4S2, because it's in period 4. And then you just use the alpha principle from there. So after 4S2 would be 3D10, 4P, whatever. So like if I asked you to do, say, antimony right here, you would do krypton, 5S2, 4D10, 5P3. So now you know where to get back on track on that diagram, and then you could just immediately use the aufbau principle. All right. Hopefully nobody laughed at what webcomics I read at the top there, when that was on the screen for a second. They're all nerdy, stupid comics anyway. If you don't read like Order of the Stick or SMBC or XKCD, I don't know her. I'm sad. Yeah, you could rewind and see what's on. There's nothing on my browser taskbar that I care that you see. Although OGLAF is not safe for work. I just find it hilarious. Where am I? I gotta get back to this screen so that I can advance the slides. So, again, using this schematic for writing electron configurations is way easier. And so from now on, what I want you to do is use the shortcut configuration. On Canvas or any assessment, what I'm going to do is I'm going to say specifically, use the shortcut configuration, because I can't program in this giant-ass answer and expect that you will not make a typo, because that's not really fair if you lose a space. But asking you to type in brackets xenon 6s2 is way more manageable. So while I go 10 to Steve, what I want you to do is use the shortcut configuration for these 4 elements. Ignore the part that says xenon, because on the previous slide that I was referring to, it was asking, hey, draw the electron config for xenon. For something like xenon, and I'll actually do that for an example right here, you can't do this. You're not allowed to do that, because that doesn't help anybody with anything. That's just like saying 7 equals 7. That's not... It's true, but it's not helpful. So whenever you have a noble gas, what you have to do when you write this electron configuration, you have to go back to the previous noble gas. And that would be krypton. And then you continue from there. So that would be 5s2. Oops, hold on. So 5s2, 4d10. And then 5p6. So that would be xenon. All right, so write the electron configurations for those 4. Use the shortcut method. Type the answer in the chat when you are finished with it, and we'll go over the answers in just a second. All right, I see some answers in the chat. I actually don't know the answers off the top of my head. I had to research them to see if they're right. And I think, for the most part, these look all right. There is a mistake on the dubnium one. So DB, don't forget the actinides. So there's got to be some F electrons in there. But I'll give you 1 or 2 more minutes to finish up, and then we'll go over the answers. And we're going to talk about transition metals and why they're dumb. And I'm saying that kind of tongue-in-cheek because transition metals are the entirety of my academic career. So I spent years studying transition metals, and they're dumb. I'll just say that. They're dumb. They're awesome, but they're dumb. All right, I'm back. Sorry, I'm talking to Steve again, and Steve does the same thing that I do, but he uses a different method, and he didn't hit record to post his lecture online, and so now he has like half a lecture, and the other half won't be posted. And all I can really say is, and I'm sorry. I hope it works out for him. But yeah, so what you do when you are figuring out these electron configurations is you pick the noble gas before it, and then you just have to use math to determine how many electrons you have left. So like if you had, say, well, I mean, we're going to do a bunch of examples here, so let's just do that on the preview here. All right, we don't need our orbital diagram anymore. No, Steve is geology. This is Steve Powell, who's in chemistry. Steve is like my best friend in the chemistry department. We do all sorts of stuff together. Like we play games, we do escape rooms. Oh, I can't see where I'm drawing because it's behind the practice problem. So let me do. Okay, there we go. I won't draw in that space. So if I do germanium here, and I look at the periodic table, so germanium is element number 32. I'll just write that down right here. what I want to do is choose the noble gas that comes before it. So I have to pick the noble gas with a lower number, which is argon. So that would be the first one I start with. So argon is the closest noble gas before. I can't go ahead and subtract electrons. That doesn't work. And then after argon, I would go to the next row, which is period 4. And I just start filling in my electrons. So 4s2, 3d10. And I'm going to keep doing this until I run out of electrons. Which is how many? So this is 18, 20, 30. And then it's germanium, so I need 2 more. So it'd be that. And there you go. So that's how you do it. You do have to do a little bit of algebra and math here. And it's just counting, really. But I say it's just counting, really, but counting is the one thing that messes me up when I do this. Like, I can do all the chemistry just great, but I hate counting. I'm so bad at it. Hooray, we understand. That's why we're doing this this is the whole lecture, is just, let's learn how to do electron configurations, because this is the sort of thing where it makes no sense in the first 10 minutes, and by the end you can totally do it. You can do it for any element. Because we just have to do 30 examples. That's really what we have to do. So for mercury, let's find the nearest noble gas. So mercury is number 80. The nearest noble gas comes before it is xenon. That's 54. And then after xenon is 6s2. And then I go dip down to the lanthanides. So I do that, 4f14. And then I come back. And I have, what is this, 5D? I don't have the little diagram. I have this memorized, so it takes me a second to do the thinking. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. So that should be mercury. And I think I saw somebody write that. Yeah, that's the correct answer. And then we have this. I don't know what this is. Or even who dubnium was named after. I know it was not George Bush. I can tell you that much. Anyway, let's find the nearest noble gas. I'm going to guess that that's radon, because this is radioactive, yeah. It is. So after you go past 7s, the next one would be 5f, because of that diagram that I showed. And then after 5f would be 6d. And then after 6d would be 7p. And then presumably you'd go to 8s after that. However, there's an interesting consequence after 7p, and that is the periodic table stops. Why does it do that? Because we haven't observed any element past that. And if I show you a periodic table, which we're going to do after this, you'll see why it stops at 7p. 4f14 has 14 electrons, because remember that for 4f, there are 7 orbitals. So here's our m sub l's. -3, -2, -1, 0, 1, 2, 3. So that's m sub l. For this, L equals 3. You went to 13s. Now, there's another problem, and that is that we had to start adding in g orbitals and h orbitals and stuff like that. But the periodic table gets very funky past 118. Where was I with radon? Let's see here. So 7s to 5f 14. 1, 2, 3. 6p3. 4f is an n equals 4, yes. So that first number right here, that is always n. What's the last one? Cesium? Oh, cesium's really easy. That's just xenon 6s1. All right, so that is how we do the electron configuration for any element using the shortcut. Okay. Now, remembering how many of each electron is in each type of orbital is just something that you're going to become accommodated with eventually. I don't have something P6 on here. But so remember that for an s orbital, there's only ever one box. I just wrote s twice. For a p orbital, there are 3 boxes, so you'd only have 2 electrons in that. You'd have 6 here, though. And then F down here would have 14 electrons. All right, let's talk about why transition metals are weird. So, because all of the orbitals tend to mash together after n equals 3 and 4 and around there, the d orbitals end up being higher in energy than the 4s orbitals. And because of that, and also later on, like comparing the 5s or the 5s orbitals to the 4d orbitals and things like that, they're so close in energy that you end up getting really interesting effects. And so there's a lot of interesting chemistry that can be done with transition metals, just because the orbitals are so close together in energy that you have a whole like spectrum of possibilities. And so if you're doing catalysis and you do a reaction and it doesn't work with, say, nickel, you could try the next element up or down the periodic table, or even left or right, to see if that works, because the energy levels are not that different. That being said, you end up with some... Why do I have this red dot on my screen? Oh, it's just something selected. That being said, you end up with some interesting sort of irregularities, we'll say, with transition metals. I forgot about this slide. I hate this slide, and the reason for this is because this is a third-year topic they're trying to teach in the first year. So what I'm going to do is I'm going to highlight the part that we're going to use for this class. That's this right here. And then I'm going to take the black highlighter. That's not the black highlighter. I'm just going to do this. So what I'm crossing out here, this is something called Slater's rules. And what Slater's rules talk about is how to determine valence electrons for substances that are not transition metals, and then how to determine it for transition metals, and how it's slightly different. For our purposes, in this class, you're only going to need to know this yellow highlighted part. Your textbook, however, treats transition metal d electrons as valence electrons, and it treats lanthanides f electrons as valence electrons. And while that is technically correct, for our purposes, that just sort of fucks everything up. So we're going to ignore that. And I just saw your comment about period number correlates with energy level, and that is correct, yes. So everything on period 4 on the periodic table, the highest occupied orbital n level is n equals 4. Now, that's not necessarily the highest energy, but it's the highest occupied n. And that's going to be relevant for here on this slide right now. Since we're really only going to talk about main group elements, but we are going to talk about transition metals a little bit too. What we're going to do is we're going to consider the highest energy level electrons in N to be valence electrons. And that'll be true for any atom that we look at. The slide, or the part of the slide that I just blacked out over here, you'll talk about this in 361 if you take Chem at UW. They'll talk about Slater's rules and how electronegativity and electron configurations and ionization energy and all that behave for transition metals. And this is something I studied extensively. But for our purposes, this is just too much detail, and it's just going to confuse us. But for everything that we're going to learn in this class, using this rule at the top here will help us. Now, what are we caring about this? So these are what are known as valence electrons. Oops, wrong color. Hold on. Valence electrons, that's also the wrong color, but that's okay. Valence electrons are the electrons that are the outermost electrons of an atom. And we're going to focus exclusively on valence electrons in chapters 4 and 5. These are the electrons that we care about for bonding. And the only electrons that we use for bonding in this class are valence electrons. And again, to go beyond the scope of this class, d electrons do participate in bonding for transition metals and stuff. But again, that's third-year chemistry. And we don't need to worry about that shit right now. Any electron that is not a valence electron, that is, not in the highest n, is instead a core electron. So when we count valence electrons for elements, what we're going to do is write out this electron configuration, such as this, and then I'm going to just count everything in the highest n. So everything I've highlighted is in n equals 2. There are 7 electrons in there, so fluorine must have 7 valence electrons. Let's do another example here. Where's my pen? I have the highlighter selected. There we go. So for instance, if I wanted to count the number of valence electrons that, let's say, iodine. Oh, iodine also has 7. That's boring. Let's do lead. How many valence electrons does lead have? And so what we would do is we would count its valence electron configuration up to xenon, which is the nearest noble gas before it. And then I would say 6s2, 4f14, 5d10, 6p2. I think that's right, yeah. Of all of these numbers that I have drawn... Oops, I accidentally underlined something. What is the highest n? Type it in the chat. What's the highest n that you see written down? Not necessarily the highest electrons, but the highest n. Very good, it's 6. Which valence electrons are in n equals 6? That's these two right here, and these two right here. And so what I would do is I would say that Pb has 4 valence electrons. And the reason for that is because there are 4 valence electrons that are in the highest n. N equals 6. Now your textbook's going to want... Oops, I didn't mean to do that. Your textbook is going to presume that you're counting valence electrons using its Slater's rules. But for our purposes, if I do something like this... Here's nickel. Nickel is argon... Oops. I looked at the periodic table and I lost track of where I was on the tablet. So here's nickel. And what your textbook is going to do is it's going to say, oh, you're going to include the d electrons in there. So it's going to say, oh, I want these. So it should have 12 valence electrons. And what I'm going to do is I'm going to say, nope, we're not going to do that in this class. We're only going to follow the rules that I set forth, which is just the highest n. And we'll say that there's 2 valence electrons for nickel, because for our purposes, that will serve us enough. Now, I want to emphasize, this is the correct answer that I'm crossing out. But for our purposes, when we're counting valence electrons, because we're going to do stuff with transition metals, such as ionize them. And the rule for ionizing is you take away valence electrons first. And if we count these guys as valence electrons, then it's just another rule that you have to remember. Like, oh shit, for d electrons, I gotta get those first instead of 4s. Alright. Lots of text appeared over what I drew. Alright. When you are counting valence electrons, anything that you do not count as a valence electron is a core electron. And what core electrons do is, well, nothing. They just sit there. They're buried underneath all of the other valence electrons, and you can't see them from the outside. In other words, if I drew a picture of an atom like this, here's my atom, here's my other atom, and these two atoms bonk into each other, only the electrons on the outside will interact. So if I was going to form a bond, it would be these guys that form a bond, and not the ones in the center. So the valence electrons will interact with my atom, but the core ones will not. All right. So for these examples, what you can do is write out the electron configuration and then identify which electrons are valence electrons and identify which ones are core electrons. Again, remember highest N. I'm going to let you do that because we're going to run out of time. I do want to finish this section before we go. Let me just check to see how many slides I have left here, because we should be very close to being done. Yes, okay. So I'll let you try these on your own time. Let's talk about the transition metals. Transition metals are weird, and the reason for this is because of how closely all the energy levels crunch together in n equals 3, n equals 4, n equals 5, beyond. If you... Yeah, sure, if you bring it up next week during the Q&A, we can go over it then. So here are some exceptions that occur with transition metals. And the first example we're going to use is chromium. And so you might say, oh, chromium, I can do that because we just did a bunch of examples with it. So chromium would be, let's write him down here. What's the noble gas that comes before it? It's argon. And you might think, okay, I'll just write this. No problem. And it turns out this is not what we observe. Here's what we instead observe. And you might think to yourself, well, what the hell? That doesn't make any sense. Well, I'm going to show you something that will hopefully make it sound like it seem like it makes all the sense. So let's do this. We'll just shove this near the top here. And we'll delete everything. Alright. So if I draw my energy diagram like this, and remember how we said that for n equals 3 and n equals 4, they were really close to each other in energy. So much so that 4s came down here, and 3d was just above it. So these are different in energy, because you can see that one is higher than the other. But in the grand scheme of things, so like 1s is way down here. In fact, it would be even further down. In the grand scheme of things, this energy gap is small. In fact, it's so small that if I put them next to each other like this, to the perspective of the electron, it's like they're almost degenerate. And so that when I start putting in my electrons, we would think, oh, okay, I'm going to do this sort of thing. This is what's happening. But remember how we talked about orbital penetration and how everything spreads out when you put electrons in here? What actually is happening is that these energy levels are coming down in energy, and so they're actually sinking further down. And what ends up happening is as I add electrons in here, these become relatively close in energy. And this electron hops ship. I missed where I was drawing. And goes here. And so this is a very complicated quantum mechanical thing that is happening. But the take-home message is that if you have either of these configurations for your electron configuration, so you're either an element that lands in the column with D4 or D9. then this is what we observe. So if you land in a column that's D4, so like chromium, molybdenum, tungsten, whatever SG is, I don't know. That's the D4 column. Or if you land in the D9 column, which is the, where is it? The copper, silver, and gold column. What ends up happening there is instead of having D4 or D9, you take an electron from the s orbital before it, and you become either D5 or D10. And that is just what we observe. And the reasons for that are because of this almost degenerate situation. We just move an electron from the s orbital into a d orbital. Now, for the 10 electron situation where everything is already paired, why would I pair one with another? That's a lot more complicated. That has to do with sterics and space and how all of those things combine together. And I don't want to waste your time explaining that. I'll just tell you that this is what we observe. And I call this the D5 or D10 rule. Is you want to land on D5 or D10 if you can. And you could borrow an electron to do it. Now, the explanation for this is not, oh, because D5 and D10 are more stable or something like that. Well, I mean, they are more stable, but it's not because they want to do this. They want to have a half-filled shell or a full shell or whatever. That's not a reason. Atoms don't want things. This is just what we observe. It is the stable form. And the reasons for that are quantum mechanical in nature, and they mostly have to do with electron repulsion. All right. So my slides here are a little bit misleading here. When it says, hey, if we land on these, it's more stable. It's not because landing on these is more stable. It's just as a result of the effects that go on, we land on these quantities. Now, this is only true for transition metals. Okay? So don't go D5ing and D10ing everything. And don't try and apply this half full, completely full pattern to any other elements, because it doesn't work. I didn't do this. Oops, wrong one. There we go. So again, if we end up on a D5 or a D10 configuration, that is the most stable configuration for the atom. It's not because of this. This is the result, is what I'm trying to say. And then there are more exceptions after this, which we're not going to cover, because they're just weird. Like ruthenium, for example, doesn't follow any rules. It's just like, I'm going to just take electrons from everyone. And then there's like one d electron and one s electron and one f electron, and like, what the hell? The lanthanides are even weirder, and everything falls apart. So basically what we're trying to do is we're trying to pin down patterns that are reproducible and predictable. And the landing on D5 or D10 rule is really the only one that I'm aware of that always happens. So this will happen with 5s and 4d. So I'm not putting the n number in front of these because this happens no matter what the n is. So if I had like gold, which is in 5d, it would take an electron from 6s, and it would be 6s1, 4f14, 5d10. And whatever noble gas is in front of it. Probably xenon. Yeah. All right. So on these slides are some expected electron configurations. I do want you to do these. So again, write out the electron configuration based on what you expect it to be. Then say, oh, I landed on D4 or D9. Let's do the D10 and D5 rule. One of them doesn't actually do this. Like, it doesn't land on one of those. I just threw it in there to make sure you aren't just trying to do this all the time. So write down these electron configurations, post them in the chat. We'll go over the answers, and then we'll call it a day. Darn it, Steve. These look good so far. All right, let's go over the answers, because Steve is just going to keep talking to me. To be fair, I am also talking to him. I'm asking him questions now, too. So let's do molybdenum here. So molybdenum... What's the nearest noble gas before molybdenum? It is krypton. And so we go to the next row, which is is it 5? 1, 2, 3, 4, 5. My periodic table doesn't have the periods numbered, so I have to do it manually. 1, 2, 3, 4. 4d4. And then I would look at that and say, oh, that's a d4. I can remove one from here. And make it d5. And for silver, same thing. We got krypton, 5s2. I'll just do it the normal way. 4d9. And we'll look at that and say, oh, I have a d9. I can make a d10 if I take an electron away. That's the wrong pen. And there you go. I don't know why I'm not just doing it this way. For cadmium, cadmium is krypton, 5s2, 4d10. And you'll look at this and say, oh, I already have d10. I don't do anything. I just keep it as it is. All right. On Tuesday next week, since we're out of time today, we are going to do electron configurations for elements that become ions. In other words, what happens when we start changing the number of electrons on something? Well, you start erasing or adding in electrons. It's basically like you're doing an electron configuration for the same atom that has a different number of electrons, at least if you're adding electrons. When you're taking them away, weird things happen, and we'll talk about what that means when we discuss ionization. But please do review electron configurations. Next week, we will finish up with those. We will move on to periodic trends. We'll talk about Z effective. And hopefully, at the end of next week, we will be done with Chapter 3. Although I think we might dip into Tuesday, week 8. So, no quiz for a while, and then suddenly this really, really long quiz on a ton of things for lots of little questions. I want to thank everyone for coming out to watch today. I hope you have a wonderful weekend. Let me put the title card up. Oops, all the text disappeared. Oh no, everything's disappearing. Oh no, it's all gone forever. I'm clicking all the wrong things. Make sure to get that lab in tonight before you go to bed. Have a wonderful weekend. Stay healthy. Stay safe. Stay at home. No, I'm poor. I will not pay your loans. Dang it, Steve.